So welcome again to Astronomy Days with the North Carolina Museum of Natural Sciences. My name is Miranda, and I'm going to be your Zoom host today. And our speaker is Tony Rice, and Tony is a NASA JPL Solar System Ambassador, which is a really amazing volunteer program with NASA and JPL. He also is a contributor for WRAL TV on astronomy and kind of all those space things. And so you might see him on there if you ever watch the news. So Tony, thank you so much for being here today and telling us about the Artemis program, which is really exciting, and it's not that far in the future. So I'm really excited to hear more about it. And I think our visitors here today are too. So with that, I'm going to let you take it away and tell us all about it.
Absolutely. Let's go ahead and get started. So what we're going to do today is talk about Artemis. You may or may not have heard of it. You've probably heard of, and I've seen it mentioned in the chat a couple of places, you've probably heard of the, we'll call it a sibling project called Apollo. It was back in the late 60s, early 70s. Well, Artemis is our way of getting back to the moon. And the goal is to go back there, not only to visit, but to stay. So the goal is to get there by 2024. The plan is to put a orbiting space station around the moon, and we're going to take day trips down to the lunar surface. But that's a ways away. To get there, it's going to take some work, a lot of engineering work. So I'm going to focus on some of the hardware that's going to take us there and where we are in the testing of that, and give you a better idea of where it's coming from, where it's going.
50 years ago, we pioneered a path to the moon. The trail we blazed cut through the fictions of science and showed us all what was possible. Today, our calling to explore is even greater. To go farther, we must be able to sustain missions of greater distance and duration. We must use the resources we find at our destinations. We must overcome radiation, isolation, gravity, and extreme environments like never before. These are the challenges we face to push the bounds of humanity. We're going to the moon to stay by 2024, and this is how.
This all starts with the ability to get larger, heavier payloads off planet and beyond Earth's gravity.
For this, we designed an entirely new rocket.
The Space Launch System. SLS will be the most powerful rocket ever developed.
And with components in production
and more in testing,
this system is capable of being the catalyst for deep space missions.
We need a capsule
that can support humans from launch
through deep space and return safely back to Earth.
For this, we've built Orion.
This is NASA's next generation human space capsule.
Using data from lunar orbiters that continue to reveal the moon's hazards and resources.
We're currently developing an entirely new approach to landing and operating on the moon. Using our commercial partners to deliver science instruments and robotics to the surface, we are paving the way for human missions in 2024.
Our charge is to go quickly and to stay, to press our collective efforts forward with a fervor that will see us return to the moon in a manner that is wholly different than 50 years ago.
We want lunar landers that are reusable,
that can land anywhere on the lunar surface.
The simplest way to do so is to give them a platform in orbit around the moon from which to transition.
An orbiting platform to host deep space experiments and be a waypoint for human capsules. We call this lunar outpost Gateway.
The beauty of the Gateway is that it can be moved between orbits.
It will balance between the Earth and Moon's gravity,
in a position that is ideal for launching even deeper space missions.
In 2009, we learned that the moon contains millions of tons of water ice.
This ice can be extracted and purified for water. It can be separated in oxygen for breathing or hydrogen for rocket fuel.
The moon is quite uniquely suited
to prepare us and propel us to Mars and beyond.
This is what we are building.
This is what we're training for.
This we can replicate throughout the solar system.
This is the next chapter of human space exploration.
Humans are the most fragile element of this entire.
So that kind of gives you an idea of what we're up against here and the reason SLS exists. So I'll answer one question I get off the cuff almost immediately. How does this differ from some of the other rockets that Under development, there's a number of, they mentioned commercial partners there that are developing other systems. SpaceX is one that comes up often. SLS is a different rocket. It is on par with the Apollo program, with the Saturn V rocket. It is a heavy lift rocket, so its purpose is to lift very, very large payloads. Those commercial partners are going to be a big part of this as well. We're going to need to get things to the surface of the moon. So the reason the Artemis program was named the Artemis program is it's named for the twin sister of Apollo. And that's really, really important. One of the other questions I saw come up in chat was about, hey, how do I become an astronaut? How to become a part of this? Can I be a part of the Artemis program? The initial set of astronauts that are going to be part of that Artemis program have been selected. And you might have seen her picture on my very first slide. Christina Koch, our own North Carolinian astronaut. She's an alumnus of NC State, and she also went to the North Carolina School of Science and Math. She was one of those first astronauts selected. But the astronaut program is adding to its ranks periodically every couple of years, so keep an eye out for that. One of the first things that's very, very different about Artemis is in the past when we went to the moon, we went to kind of the easy places, easy in terms of the engineering. We went to very flat places. We tried to avoid landing on craters. It was our first time there, so we made perhaps not the most geologically interesting, but it was a little bit more easier with the engineering. This time we're going to the South Pole. We've never been there before. In this next video, it doesn't have any audio with it, but I want you to watch what's happening with the shadows. This was taken from the Lunar Reconnaissance Orbiter, and it's showing what's going on the south pole of the moon. Notice that there's parts of these craters that are always in shadow. That's where we're finding the water ice. And the water ice is really, really important both for drinking. If we split it into its hydrogen and oxygen components, the hydrogen can be used for rocket fuel, so we don't have to carry the fuel with us. We can produce it there. And the oxygen can be used for breathing. So it's pretty important to have access to water ice. And we found that there's a lot of it there. So moving on, let's talk about the pieces of the SLS system and what it's going to take to get us there. The steps that have happened already in testing and what's yet to come. So the first is the solid rocket motors. These will look familiar to you if you're familiar with the Space Shuttle program. They are reused from the Space Shuttle program. They're a little bit different in that each one of these are sections. You can kind of see the lines in there in between. We've added additional segment in here to give it that much more thrust, a little more burn time when we launch them. The big difference between the Artemis program and the Space Shuttle program when it comes to these solid rocket motors is we are not going to retrieve them. They will end up in the Atlantic Ocean. They'll eventually sink. They become really nice artificial reef for fish. So they do get reused in that regard. It's kind of interesting how they get down to Florida for launch though. They are tested and fueled in Utah. At a facility up there that's not that far from Promontory, Utah. But you think back to your history classes and the Transcontinental Railroad where it first met, that's about 10, 15 miles away from where they test these. I found that kind of cool. But this train runs across from Utah on down to Florida. They call it the rocket train. Those white canisters there are what are holding the segments of the rocket. And then they have boxcars in between to space them out. There's a couple of bridges they have to go over between Utah and Florida, and that keeps the weight spread out so they don't cause any problems. We've already tested this fully built up version of the solid rocket motor, and I'll share that test with you right here. So this is back in September. This kind of engine, you light it and it burns until it burns out. You can't stop it. Very much bolted down to the desert floor. It's aiming that exhaust up the side of a mountain. The heat there is just incredible. It actually creates glass. And the engineers will go and collect up after that glass after a test like this, and they have it sitting on their desk. But you can see the scars on the hillside from previous tests. This is necessary to make sure that that new configuration of the engine is working as planned. When the rocket has spent all of its fuel, and the fuel inside is solid. When they first put it inside the inside of this engine, It's about the consistency of silly putty, if you've ever experienced that. What's actually burning is aluminum. That's the actual fuel that's being burned here. It's bound with an oxidizer. So this is SLS all stood
Sorry,
up.
Tony, we had a question about the fuel.
Oh, please.
And, did you say that the fuel completely burns up? And so when it falls into the ocean, you know, we are a science museum, so we want to make sure that we're not just contaminating the ocean with some unspent fuel.
Of course, and we've been doing this way since the space shuttle program. So the fuel does completely burn up. Back in the shuttle days, we would retrieve these engines and tow them back to shore with a boat and take them back to Utah, refuel them. The fuel inside the hole that's bored up through the middle of that fuel, there's engineering involved there too. The shape of the hole determines how fast it burns and what kind of thrust. You can have different shapes throughout this engine to kind of control the thrust. You can throttle it up, you can throttle it down during that burn time. But yes, all of the fuel does burn up. It's not an ecological hazard at all.
Very cool. And it does seem like it is very, very hot, that anything within a small space of it that is flammable would just burn up too.
And it does cool down quite a bit because after all that fuel is spent, it does come back down to the surface of the ocean on parachutes. So it has some time to cool down as well. And the nice cold Atlantic does a good job of cooling it the rest of the way.
Just a quick follow-up. Tina wants to know, how do you hold that thing down to keep it from like shooting forward during this test?
So if you look here, it's kind of hard to see. Those are the hold down bolts, and these bolts themselves, they're probably about 3 or 4 times as big as your arm, and really, really big bolts on top, really big nuts holding all down. So it's held down pretty well.
Cool. All right, thanks.
Good questions. So this gives you kind of an idea of how big it is. And one thing to note here, NASA fans might be excited to see that the worm logo is back. NASA has 3 different logos. They have one that you rarely see. You might see it on flags during press conferences and things like that at NASA headquarters. That's the internal kind of official headquarters one. You've got what we call the meatball. And if you've got your video on, you see I'm wearing my meatball shirt today. That's the blue NASA logo with the red swoosh through it. And then you have what we affectionately call the worm logo. This was popular during the 80s. And we've gotten away from it a little bit, but it's making a comeback. So you'll see that on there. These black and white markings that you see on here, those are used as calibration marks. We have very high speed cameras, very high resolution cameras that are watching these liftoffs, watching these launches. And these registration marks tell us exactly where in 3D space that rocket is. You can see them up here as well. That's the purpose of those. SLS is a little bit shorter than Saturn V, at least the version that we're going to be launching next. It can get bigger. The whole purpose of this rocket is to be a general purpose heavy lift rocket, not just to take us back to the moon, but this is the rocket that we can use to take us to Mars using a full complement crew in that Orion capsule. It's going to produce more thrust than the shuttle, and even more than the Saturn V. And the Saturn V to date has been, one of the most powerful rockets that's been available. And what it's mostly about is this cargo capability. We can take more than 27 tons, and shuttle only could take that to low Earth orbit. We can take even more all the way to the moon. This is another view of how big these things are. Have you ever seen the shuttle roll out of the vertical assembly building down in Florida, that giant building with the roll-up doors that they stack these rockets? That was built for the Saturn V, so it's built to handle a vehicle that tall. The shuttle looked itty-bitty coming out of that thing. Right now, we're already starting to stack Orion, the Block 1 version of Orion. We've got the solid rocket motors that are stacked. At some point in the future, and we'll talk about when that's going to be, this core booster right here, the big orange piece, is going to be heading down to Florida, and it'll join the stack. So these are the pieces, parts. Let's talk about the components, and let's talk about what is tested when. I already talked about the solid rocket motors. There's 2 of those, are solid rocket boosters. We've tested those. Those are good. They've been shipped down to Florida. They're stacked. They're ready to go. The core stage, we're in the process of testing right now. I'll show you one of those processes. A little bit in flux there. I'll share with you what's going on there. The RS25 engines down at the bottom, there's 4 of those. Those are actually recycled shuttled main engines. They are the most powerful, most efficient liquid-fueled engines ever built. They were recovered after every shuttle mission and refurbished in one of the cleanest shops I've ever walked into. You can literally eat off the floor of this engine shop. We've got plenty of them available for the planned Artemis missions, and they're building some more. If you've ever had the opportunity to see a shuttle orbiter on display at a museum, there's one up in Washington at the Air and Space Museum there at the wing that they've got out by the Dulles Airport. If you've had the opportunity to go down to Florida at the Kennedy Space Center, Atlantis is down there on display. Really, really neat display. There's one in New York. There's one in California. The engines that are on those orbiters are mock-ups. And the reason they're mock-ups is because these are very good engines. We want to reuse them for this program. I'll say right now that this is an expendable rocket where we were able to reuse the engines on the shuttle because it returned back to Earth like a glider. That's not the plan with SLS, and the reason being it's about the mission. We could possibly reuse those things, but we wouldn't be able to lift as much of payload. So it's a decision that has to be made. The other parts that are going on here are the launch abort system. I'll show you that in a minute. That's basically to pull the astronauts off of what is essentially a giant bomb should the need arise. And that can happen on the pad or during ascent as well. And then the Orion crew module that you saw mentioned in the video. We've done that pad abort test, testing that launch abort system. We've tested the parachutes. We've tested those RS25 engines. We've tested that the ascent abort mode there. We've tested the fuel tanks. I'll show you some images from that. And I showed you the SRB test in just a moment ago. So let's look at what's going on here. So this is those 2 fuel tanks. Now, these liquid fueled engines run on 2 types of fuel, and they're what are called cryogenic fuels. They're super cooled. The reason they are cooled so much is so that this gas will go into a liquid form and you can get a lot more energy in a lot smaller space. So the liquid oxygen test was tested back in 2020, June of 2020, and more than double of what the expected flight loads it was able to sustain. So it's a smaller of the 2 tanks. What they did, this happened down in Huntsville, Alabama. They took a flight model tank and they pumped it full of water until it broke, basically. Did the same thing with the liquid hydrogen tank. That's over here on the right-hand side. I was down in Huntsville when they were first starting to build this rig to be able to test this, because that liquid hydrogen tank is just absolutely huge. Same idea, you pump it up to pressure and beyond what is expected, so you can be sure that it's going to be able to safely hold those loads. Again, this is back in December 2019, it again far exceeded the loads that it needed to be able to handle. Each one of these tanks can be filled and drained 22 times. And the one that we're working with right now has only been filled and drained twice, so we got lots of life left on it. I'll jump into the RS25 engines. And I'll give you a little tip here. If you ever see a picture of a rocket engine, particularly at Rocketdyne, which is a contractor that works on these engines, and it's not just these SLS engines, they work on engines for the military and other commercial partners as well. If you ever see an engine, a picture of an engine where the bell is facing down, the bell is that black kind of conical looking part. That's where the exhaust exits from. If you ever see it facing down, well, that's the same way it's going to be in a launch situation. That is an engine that is going to have humans on it. They want to test it in a way that ensures, or want to work on it in a way as well, that ensures that you're testing as you fly, they say. So that's just a little tip there. Since the shuttle program, Aerojet Rocketdyne, I was down there about a year ago at their facility in Mississippi where they do all these tests and talk to some of the engineers. They've gone through and reduced the weight on that engine. Reducing weight when you're talking about space travel is really, really important, because every ounce of weight that you have that's aboard the rocket and is serving the rocket, well, that's an ounce of payload that you can't take up there. That's an ounce of people that you can't take up there. So you want to keep the weight of the vehicle down as much as possible. So you see some numbers here on weight reduction. And that was achieved through 3D printing in a lot of cases. Instead of milling these things on giant machines out of solid blocks of aluminum or titanium, they're building them up out of 3D printed materials. It's proving to be a pretty good weight savings. So I'll show you one of the engine tests. I mentioned that we test the rocket engines individually, and I'll let that run for a little bit. And while that's running, Miranda, were there any other questions?
Yes, so John wanted to hear more about how the LAS, the launch abort system, works.
Oh, good question. I've got a couple of slides that talk about that. And I got a cool story about the launch abort system as well. So what you see here, this is happening down in Mississippi at the Stennis Space Center. It's basically in the middle of a swamp. NASA has been testing things there since the Apollo days. We test lots of other rocket engines there. There's lots of other federal agencies that work out of there. They actually make passports there too. I find kind of interesting. The Navy trains there. But you run engines in these test stands. Again, they're bolted down so they don't fly away. It creates these beautiful rainbows because when that liquid oxygen and liquid hydrogen comes together, it creates water. It creates these clouds. So on days that these tests run, they create clouds over the Space Center there, and it rains sometimes. You may notice the river that's next door. That serves two purposes. That allows them to draw in water ahead of the test and be able to pump it into what's called the flame bucket down there at the bottom. That serves partially to cool the exhaust there, but it's mostly to be able to spray water into the exhaust to allow the sound to be dampened. Otherwise, the sound from the engine alone could shake this entire thing apart. So let me show you the green run that happened just a couple of weeks ago. So what you just saw was a single engine running. So the green run is when we took the core booster, all four of those RS25 engines, and we fired them all at once. And the idea that we were going to run it for 8 minutes, which is the time that it would run on a normal launch. That would be the full duration time that those engines would need to run to get that booster into orbit or get the payload into orbit. I'll tell you right now, it didn't go quite as planned. It ran for a little over a minute. They were planning to run it the full 8 minutes. Right now, NASA is evaluating the data that came out of this to determine if they have enough information. Again, those individual engines have all been tested. This was a full-up test where not only those four engines are working together, but all the avionics and all of the other computers that make this thing work. That was the purpose of this test, having everything work together. It's an integration test to see if they got enough data out of that to give them the level of comfort to ensure that we'll be okay to move on to the next phase. So let me show you a little bit of that. The sparklers you see there, that's burning off excess hydrogen. As that fuel turns, that hydrogen turns into a gas. We ran all four of them at once. This is the same test stand that tested the Saturn V rocket back in the mid-60s. Again, the steam you're seeing being created, it all just shoots out into the swampland there. I've been to this test stand as well, standing about where that sign is in the lower portion of your screen, lower center. There's those four engines running all at once.
So Tony, can you remind us what kind of temperatures we're reaching with these rockets?
I don't have that off the top of my head. I'd have to, maybe at the end I can look that up. It's hot. It's very, very hot. But we actually saw the cloud that was created here on a weather satellite immediately after this test. It was that big. Yeah, nobody's around here. They're all in bunkers, and they're a good mile or so away from this test site. So the crew capsule has to be tested as well. And that was done back in December of 2014 using a Delta IV Heavy rocket, which is one of the more powerful heavy lift rockets that's out there right now. We took a trip around the Earth and then landed off of the coast of coast of San Diego, brought it in. That was a test there. And the launch abort system, somebody asked about that. I took a couple of screenshots here. Didn't work really well over Zoom to show you the video. It was pretty jerky, so I did it this way. Basically what a launch abort system is a couple of very, very powerful rockets that are mounted on top of the crew capsule. This is jettisoned after it's not needed anymore, but when it's needed, it's needed. This is called a tractor system. There's two types of launch abort systems. There's a tractor system that pulls the capsule off, and then there's a pusher system which has those rockets mounted beneath the crew capsule, and the SpaceX Dragon uses a pusher system. Pretty much everything else uses this tractor system. The image in the middle you see there is that launch abort system firing and pulling that capsule off, and the image over on the right-hand side is this coast phase after the engines have done their job, pulled the capsule away from the possible danger of maybe an exploding fuel tank or something like that, and would then be falling back to Earth. The parachutes would deploy and cushion the landing. That being said, if I were an astronaut aboard this thing, I would not want to be around when this launch abort system fires. The G-forces are 10, 12, sometimes as much as 14 Gs. The expectation is that if there is an astronaut aboard here, they are probably going to break some bones. They are probably going to have quite a bit of problem breathing while this is happening, but they're going to survive. This has to be this way in order to get them away from that dangerous situation as quickly as possible. Launch abort system is only fired once, and it wasn't with an American rocket. It was with a Russian rocket back. It was the Soviet Union rocket. And the story I like to tell about this is the Russian astronaut who was aboard that flight where a launch abort system, it was technically a pad abort because they hadn't actually launched yet, but there was a reason to get the astronauts off there very quickly. They fired the pad abort system. It pulled the capsule away. They were able to land safely, and the crew lived. You fast forward to the fall of the Soviet Union, and that astronaut was visiting Houston, was visiting Mission Control, still a part of the Russian space program, as we were running up to the current International Space Station program, where we're now in cooperation with the Russians, had the opportunity to meet the gentleman who had designed this system. The Russians copied the Apollo built, or the Apollo design for the launch abort system. So he got to meet the NASA engineer who had designed this. They both had, conversed with each other previously, but they never actually met each other. So picture this giant Russian guy and this little American engineer more or less running to each other at the front of Mission Control, and bear hugs. They were so glad to see each other. And that was that astronaut's opportunity to thank that engineer for essentially saving his life. So moving on, I've mentioned parachutes as being a very important thing here. We have tested the parachutes that are going to bring the Orion capsule back to Earth. There are actually 11 parachutes. When you see the pictures of the capsule on the chute, as we call it, coming back to Earth, you count 1, 2, 3. But there's a lot more than that. They're drogue chutes. The purpose of drogue chute, it's a smaller chute that pulls the rest of the parachutes out. There's a pilot chute that actually pulls that main chute out a little bit more. And this is necessary because these chutes are so very, very big. That was all tested in Arizona back in 2017. It's kind of fun how they do it. They take it up in a cargo plane, open the back door, and shove it out. That's kind of how it works. Worked marvelously. The jobs of these parachutes are amazing. It's going to go from 26,000 some feet down to 0 feet, from 300 and almost 25 miles an hour. It hits the ground going 17 miles an hour. So they're doing a very, very important job. The way we recover these capsules is going to be very different from the Apollo program as well. Over on the right-hand side, you see the ship that we're going to use. If you think back to the Apollo program, and if you had the opportunity to go to North Carolina Museum of History back during the 50th anniversary of Apollo, you might have seen some of the things about the helicopters that were used to pluck these capsules out of the ocean and the astronauts, bring them back, set them down on top of an aircraft carrier. One of the Apollo missions was recovered by a helicopter pilot from North Carolina. So we have that connection there. We're going to use what is called an amphibious transport dock. The astronauts are going to stay in the capsule. We're not going to open the door and pull them out with a helicopter. we're going to send a crew out on these rigid inflatable boats, basically attach a cable and draw them into the deck of this ship that can be drained, and then they're going to pop the hatch open and walk out. The yellow piece that you see there is what will attach the capsule to as it's being brought back into dock, back into port, but a bit of a different way, a little more efficient that way, a little safer too. So green run, the engine or the test that we saw with all 4 engines, that is the rocket that is going to be used for Artemis 1, and I'll show you what that's going to do in a moment. That's a picture of the engines before they were installed, and you see there's a couple extras in there. Notice that they're bell down. The engines on there have quite a history behind them, and I've got the details here. They've been used on the last space shuttle launch, STS-135, a couple of them. A couple of these engines have been used in the repair of the Hubble Space Telescope. One of them, John Glenn flew on when he flew his shuttle mission. So these have quite the history, and all of the engines we're going to use in the Artemis program, at least the initial ones until we use up the existing inventory, those are going to have a big history behind them. So this leads me to Artemis 1, and this is what we are currently planning to fly in November of this year. Now, because of the less than expected runtime on that green run back here a couple of weeks ago, we may have to test that again. We may not. If we have to test it again, November is probably going to be pretty optimistic, but it shouldn't be too far after that. That same rocket that is sitting in the test stand still in Mississippi, they'll pull it out with cranes, they'll load it onto a very specially designed barge, and that will go down the Mississippi River, around the tip of Florida, and then on to the Kennedy Space Center. This will be an uncrewed mission. We will launch it, we'll take a couple of loops around the moon, we'll test all of those systems out, and then we'll return back to Earth, recover it with that ship that I mentioned before. And let me pause here and see if there's any questions about any of the tests that I've talked about so far.
I think really the only major question is kind of the environmental impact of kind of these missions and these tests and stuff like that. So do you know anything about kind of the environmental impact of all this stuff? I know like space junk is a little bit of an issue right now that we might have to solve later on. But
it absolutely is, and I'm teaching a class over at NC State on space junk, as a matter of fact, so that's top of mind for me. We did a pretty bad job of cleaning up after ourselves in space during the 60s and 70s. Actually, the third thing that was ever launched, the first thing or the second thing by the United States, is still in orbit and will probably still be in orbit for another 40 or 50 years. Since then, we've learned a lot about space junk. So any of these things that you see being jettisoned along the way, like this trunk right here that would be connected to the Orion capsule, those have been designed in a way that they will deorbit sooner rather than later. They might stay up there for a couple of weeks, but they're not going to stay up there for a couple of years. Even SpaceX lands their boosters and reuses those boosters. Every single SpaceX launch produces at least one piece of space junk, and it's that second stage that stays in orbit for several weeks. So where I'm going with that is things are now designed so they don't stay up there as long. It's a conscious effort. And other stuff that has to be jettisoned along the way, it is designed to go into primarily heliocentric orbit, which means it's in orbit around the sun, and put into a place where it's not going to be a danger to any of our satellites, even out to geosynchronous or GPS heights of orbits. It's not going to be a danger to them. And the environmental impact back on Earth, all that steam that you saw coming off of the engines during that test, that's all just water, 100% just water. Even the burning of the solid rocket motors and that aluminum. If you've ever been to a space shuttle launch, you may see that there's a warning about the possibility of, if there isn't an incident, if there were an explosion during launch, that there's a possibility that actually acid rain could be created by the burning of that fuel so low in the atmosphere. But the acidity of the rain, the pH of that rain, is actually a lot better than what it gets produced out of your average factory here. So the impact is pretty minimal.
And Jenny wants to know what degree paths typically would be participating in a class about space junk.
Ooh, it's a new concept. It's a new focus. And one of the things, I've talked to one lawyer that specializes in it, and even he admits there's not a degree program in it. There's not a custom path that you can follow. He kind of followed his interest. He had an interest in the law, and he had an interest in space. But it is growing. The way space law works with space junk, if there is an incident there, if there is some sort of we call them conjunctions, where two spacecraft try to occupy the same space and end up taking two perfectly good spacecraft and turn them into a couple thousand pieces of debris. If that happens, whoever is at fault there, the country where the vehicle was launched from, they're responsible for it. So that's happened a couple of times. An Iridium satellite, which is basically a very expensive works anywhere cell phone, used a lot on ships. An active Iridium satellite hit a no longer active, a dead Russian spy satellite. It created a couple thousand pieces of space junk. It was Russia that was responsible for that. We don't have good ways to clean that up, though. So maybe law is an answer, but the data that's involved with tracking this kind of stuff, data science is becoming a lot bigger piece of that puzzle.
Yep. It takes a lot of brains to figure out problems.
And it takes a lot of different kinds of brains, and there's room for everybody there.
Right. And we have, just to give you a time, we have a little over 10 minutes.
Awesome.
So I'm gonna be quiet and let you.
Let me show you one last video that's going to show you what that launch is going to look like, hopefully in November, of that Artemis 1 mission. Give you a flavor for what's going to go on there. And we can open up the floor for questions about this or general NASA questions or whatever. This is launching from the same launch pads where Apollo launched from, where the shuttle launched from. That white line you see there, that's a path that goes back to the launch control center in the vehicle assembly building where it was put together. There's a giant crawler that brings that mobile launch platform out.
Booster ignition and liftoff.
And that was that launch abort system removing itself. TLI, or translunar injection. That's when we fire the engines to escape the Earth's gravity and head to the moon.
And we have a question, maybe you can point it out if it comes up. Are there thrusters or anything to control where it goes, or does it only go forward?
Could you repeat the question, please?
The system, like when it gets to a point, does it have thrusters or anything to turn it, or it changes direction, or does it just go like straight until it gets to where it needs to go?
That's a good question. There's a number of engines on there. You saw the separation of that, they call it the ICPS. It's basically a second stage its purpose is to what we call delta V. It gives the proper delta V, the change in velocity, to escape Earth's gravity and be able to head to the moon. But yes, absolutely, we have to maneuver the vehicle both on the way to the moon and also in lunar orbit. To even achieve lunar orbit, you got to change the shape of your orbit in order to truly be in orbit around the moon. And that's done with a number of other engines. They're called reaction control systems. Because you're in space now and you're not in an atmosphere, fire works a little bit differently. So these reaction control systems are using what are called hypergolic fuels. And if you've ever had to fix something with something you buy from the hardware store or whatever, where it's got two tubes of liquid, you combine those two tubes together. As long as they're separate, they're just, whatever the two different compounds are. But you combine them together and they turn into this really good adhesive that even heats up a little bit. It's the same kind of basic idea with these hypergolic fuels. They're completely stable on their own, but you put them together and they explode. And that's a good thing, because if you point that explosion in the opposite direction of where you want to go, hey, you got a rocket engine in there, and you can control it pretty easily. So those RCS systems, there's a couple of them around the vehicle, allows you to point that explosion in the direction that takes you where you want to go.
Very cool. And this is a really interesting question. Are there any kind of cameras or anything in space to kind of get pictures or videos of these launches?
Oh, yeah. Yeah, I love whenever there's a launch from either California or Florida, or even sometimes from the facility out on the Virginia Eastern Shore. My go-to is I go to the weather satellites and pull images down that way. But today, the cameras that are available, and more importantly, the wireless video systems, the wireless communication systems, will have cameras on board Artemis that are looking down the body of the rockets. We'll be able to see it draw away from Florida. NASA, especially since this is the first full-up test, first launch of this vehicle, there will be a ton of cameras out there. So there'll be lots of different views that you can see there. Once we get to the moon, there's nothing pretty much in between the Earth and the moon, of course. Once we get to the moon, there's still a lot of assets that are in lunar orbit. And I've not seen the plan specifically for Artemis 1, but based on what I've seen with our going to Mars, I wouldn't be a bit surprised if some of those orbiters around the moon are taking a good look at Artemis in flight. And definitely once we get to the point of being able to take those day trips down to the surface of the moon, I know we'll have all sorts of cameras on the outside of that Gateway space station as well.
It's going to be very exciting.
And I'm game for any questions on NASA in general, or rocket testing or whatever.
Yeah, so we did have a question. Carl wanted to know, why did they cut the test short for the 4-rocket engine, or the full test in Mississippi?
Yeah, excellent question. Supposed to run at least 4 minutes. They were hoping for 8 minutes. They ran just a little bit over a minute. It was automatically ended, the test was, because a parameter on pressure in one of, I believe it was the system that gimbals the rocket, that moves the bell of the engine and changes the direction of that thrust. It went outside of a parameter. They have very strict parameters on, if pressure goes above or below this for this particular component, we're going to shut the test down, because these are engines that we want to use to launch this rocket. And the whole purpose of the test was to gather a lot of data. So it was automatically shut down. It wasn't necessarily an engine failure. It was a parameter that they weren't comfortable with, and out of an abundance of caution and safety for the hardware there, really wouldn't affect people because, you know, they were far enough away, they went ahead and shut it down. So good question.
Awesome. And Marcel wants to know how the astronauts will get down to the moon. So landing gear, or, you know, can you speak to that?
Yeah, so it's going to be a little bit similar to what we did with the Apollo program. There will be pads, landing pads, similar to the what you see on the lunar landers. We're going to have a different kind of lunar lander that will be reusable. So it will go down to the surface of the moon. The astronauts will do their science for some period of time, and then they will be able to use it to go back up to the Gateway orbiting station.
And I know you talked about some of the reuse for some of the rockets and things. So how many kind of reuses, or how many years are we looking at for a lot of these rockets?
So SLS is a single-use rocket. Its purpose is as a heavy lift rocket. So once it's launched once, it won't be reused. Now the equipment that's going to be on the moon, the resources up there, those will be used over and over again. Kind of like we stay aboard the International Space Station and are able to bring capsules back and forth. Same kind of idea there.
And okay, this is a personal question for you. What do you think is the most important part of the mission?
I think it's getting to a different part of the moon. I think it's getting to that south pole of the moon and getting beyond the science that we've been able to do at the equatorial regions where most of those Apollo missions landed. Different geology there. We have a pretty good idea of what we're going to see there because we've been in orbit around the moon with missions like the Lunar Reconnaissance Orbiter, but you just can't beat. And somebody pointed it out before we started with the Apollo 17 mission and having a geologist on board there. You can't beat having a human there, and especially a highly trained human scientist, because they're going to be able to react and they're going to be able to even change objectives, science objectives, immediately once they see something. Well, I found this makes me curious about going and looking a different way. But you know, getting to those parts of the moon that have never seen sunlight, it's just physically impossible. Since whatever created that crater back probably millions of years ago, sunlight has not touched the bottom of that crater since then. So we may find some things that are very surprising about the moon by having the opportunity to go down there in that deep in those craters, you know, like I say, that haven't seen sunlight.
You know, I think I watched a presentation earlier this week, and they, you know, showed videos of kind of the excitement of the space age in the 60s, and, you know, the whole world was involved, and it was just this huge spectacle, and everyone was excited and involved. Do you see that happening with all these new missions that are coming up, taking people back to the moon, you know, setting up stations, going to Mars? It seems like this is kind of a new age for space. Do you feel that excitement? Do you see that kind of ramping up, or is it just, do we have too much to think about and to, you know, be entertained by now?
There's a little bit of the latter, and space is different now because you know, back in the 60s, I mean, it was really only the Soviet Union and NASA in the United States, and there were what, 4 TV channels to pick from. So there was a lot more focus on it then. But yeah, I do see excitement ramping up because it's different. Yes, we're building some rockets that are comparable to the old ones because they have to be that powerful in order to complete the mission. But what's the biggest difference is, and I'll just say it, it's not a bunch of white guys. It's the astronauts that are involved with it, the engineers that are involved with this, really, really diverse. Half of the astronaut corps right now, based on the last couple of classes that they have picked, half of them are women, and that's going to continue. So when you visit nasa.gov Artemis and you go and look through some of the documents there and some of the web pages, you'll see it mentioned over and over again. Artemis is about the next step to the moon, with the next man and first woman. So the next person to set foot on the moon's surface, there's a 50-50 shot of it being a woman. And, you know, there's a pretty good shot that it might be Christina, because like I say, she's part of that first set of astronauts that have been selected for this program.
And we will for sure be following along with that as the State Museum, and we will be cheering her on. And I'm sure you can join us for some really amazing programs moving forward for all of these exciting things that are happening. And we are just about out of time. We want to make sure people can get to the next program if they would like to. And so I just want to thank you so much again, Tony. This was a really amazing talk. I am so excited about the Artemis program and what is coming up. And I hope that everyone else is, and they are ready and will be checking us out. So I want to thank everyone again for coming to this program. I hope to see you in future programs. We've dropped a link in the chat for a survey if you wouldn't mind filling that out. We'd love to hear feedback, good or bad, constructive. We just want to know how to make our programs better and how to better reach you as well. I want to thank NC Space Grant for sponsoring Astronomy Days, including our captioning. And you know, we have some really cool space gear that was designed just for Astronomy Days this year by our in-house designer, and you can pick up that gear at our store at naturalsciences.org. And you can check out the remaining programs for today, tomorrow, and Sunday. We have full days of programming, so make sure you sign up for these really interesting talks. We also are recording everything, so you can check out the recordings at naturalsciences.org. And thank you again so much for coming, and we hope to see you next time. Bye-bye. Thanks, Tony.
Thank you.